Our next talk after the break is by Davide Perego from University of Milano-Bicocca. So take it away.
Thank you, Alex, also for inviting me here to speak. So, okay. So what we're going to talk about. First of all, I will recall what hyperbolic groups are, even they were mentioned in the previous talk during this conference, and also about their boundaries. Then I will give some information on the literature of approximation and recursive representation of such boundaries. And in particular, I will tell you what I mean by these two terms. After that, we will define what the tree of atoms is, which is the main object of our interest. And I will give you some motivation on why it was introduced in the first place. And it is related to the so-called Bonigman conjecture that James, I think, mentioned 2 talks ago. Finally, I will tell you something about my work that is trying to connect hyperbolic groups together with this tree of atoms. So let's start. I just want to recall that by hyperbolic group, we mean a discrete group acting geometrically on a locally finite graph, gamma. And the locally finite graph gamma needs to satisfy the following condition on geodesic triangle. So there exists a non-negative constant delta, such that for any geodesic triangle, one side of the triangle is fully contained in the union of the delta neighborhoods of the other 2 sides. Okay, this leads to some examples. The first one is our trees, whenever delta is equal to 0. And I mean, this is an infinite tree, but you can understand it. But we also allow other geometries like this, I think, more connected graph with a more connected boundary, whatever it is. Still, you can see that there's some tree behavior inside this tree. And from a more algebraic point of view, all of these groups are hyperbolic groups. In particular, finite groups are trivially hyperbolic. Free groups are related to trees and so on. And it's a huge class of groups. But what we are really interested in is the boundary. So let's start with the definition of the Gromov product that was again already mentioned during the conference, but I take a more intuitive approach. Let's start from the boundary of a tree, which you can imagine is a counter set, because I mean, the idea, what is the idea? You have to consider all the geodesic rays starting from a base vertex x0 and going to infinity. And so you have this set and is totally disconnected because we want to measure how far 2 of these boundary points are. And the way we measure that is by considering the longest common subpath starting from x0 between these 2 boundary point gamma and eta. And so the more this Gromov product is large, the more they are close one to another in the boundary. And if you put some distance, some metric on this, you can easily see that this resembles a counter set. So what about the general case, the boundary of an hyperbolic graph? Well, in this case, you allow more connected spaces, for example, the sphere that you saw in the previous slide, but still the definition kind of resembles the one of the tree, because you still consider the geodesic rays starting from x0. And the way you want to measure now how far one is from another is similar, but in this case, you want to consider the instant such that from that instance on, the 2 rays are diverging one from another, so that it means that the distance at each step of the ray is increasing, while from that instance, I mean, before that instant, the the distance between these two rays was bounded by a constant, and so they were fellow traveling, as we usually say. And indeed, the idea of the Gromov boundary is that you consider the connection of all geodesic rays leaving X0, and you quotient that by this equivalence relation here. So you start from a ray, you consider another one, and you want them to be the same boundary point if and only if at each step the distance is bounded by 2 delta, where delta is the hyperbolicity constant. What if this doesn't happen? So what if at some point this distance grows? Well, then it grows exponentially. So we say that two geodesic rays diverge exponentially whenever we consider a path starting from here and going to this point here. I hope you can say the pointer. You can see the pointer. That is fully outside the ball of radius n, centered at our base point x0. And we measure the length of this path, and is greater or equal than an exponential in n. Okay, so these are all the features that we want for the hyperbolic groups. So let's start to see what it means to approximate and recursive present the boundary. So by approximation, I just mean some sequence of well-behaved metric spaces, or even better, some sequence of simplicial complexes of bounded dimensions that converge in some sense to the boundary. While for the recursive presentation, I mean some machine or algorithm that can tell you some property of the boundary, having an input, maybe a presentation of the group or the group itself. So I think that the first step towards this direction was due by Conrad and Papadopoulos, in 1993. They used trees that can be defined directly from the hyperbolic group. They were originally introduced by Gromov himself while defining hyperbolic groups. And what they did with this tree was to, in the case of torsion-free hyperbolic groups, they proved that the Gromov boundary was a semi-Markovian, which is a dynamical property that I don't want to go too much in details about this definition, but it will, it will be useful later to know that they proved this result. And Dominika Polik in her thesis completed work for the case with torsion, and also proved that the boundary can be seen as a Markov compacta. This is an example of approximation, because a Markov compacta is a limit of simplicial complexes of bounded dimension. But there are other results in this area. For example, the application of subdivision rules for hyperbolic groups, and also algorithm to predict whether the boundary is a circle or not by studying the Cayley graph. So a little bit more about the Conrad and Papadopoulos work. I told you that they use different trees, but I think that the most understandable one in a presentation is the one made by geodesics. So you start again from a base vertex x0, and you consider all the geodesics starting from x0, and you get a tree structure by saying that, two geodesics one is a prefix of another. Okay, and these will be something that is related to our work. But what are the main ingredients for their proof? First of all, we need a tree with some nice dynamical property. In particular, in this case, is a generalization of what is called a one-sided edge shift. But in our case, we will just speak about self-similarity of a tree. Then we want a projection from the boundary of the tree onto the Gromov boundary. And a nice way to say if two elements are in the same Gromov boundary point or not. So a nice description of the fibers. And in this process, we will dealing with machines. So what is our main object of interest? It is the so-called tree of atoms. The idea is that we want to associate a function, a distance-like function, to any vertex of the graph. And the function will go from the vertices of the graph into Z, and it looks like this. Okay, so we have our graph, we have our base vertex, sorry. And for any vertex in the graph, we associate its function here, calculated on any x other vertex in the graph. So if we change V, we change the function, as you can see on the grid. The idea is that now we want an equivalence relation, so a finite partition of vertices for any natural numbers. So, and the way we do so is by saying that V and W, two vertices in our graph, is n equivalent, are L equivalent, sorry, if and only if their distance function, the associated distance-like function, agree on the end ball of radius. So the ball of radius n centered at x0, our base vertex. And the equivalence classes are called n atoms. Let me see if I can tell you more with an example. So here the ball of radius 1 are all the dots in blue. Okay, this is our x0. And an atom is, for example, this region in yellow here, with its associated, so any vertex that belongs to this region with its associated function, distance-like function on the ball of radius 1. And so if this is another atom, if you change atom, you can see that you change the function and so on. And what happened to the second level? Well, in this case, to see if an atom in this representation, you have to intersect geodesic, red geodesics with blue geodesics. So this is an atom, this is an atom, and this is an atom. And you can see that by definition, what you're asking for is that two vertices, as the associated function to two vertices has to be the same on a ball of radius n where n is growing. And so any level n atoms will be fully contained in a level n-1 atoms. And this containment give you the tree structure that you're looking for. So now that we have defined the tree of atoms, I want to tell you why it was introduced in the first place. But before, we need the definition of an automata. I mean, there are many definitions, and I want to go through the details with ours. So in our case, an automata is a machine. So it has an input and an output. In input, we have infinite strings over a finite alphabet sigma. And in output, we have a yes or a no. And Q is a set of states that needs to be finite, while the arrow is the transition function, and Q0 is the initial state. Sorry. So how it works? We have an infinite string in input, and we want to recognize it, so a yes output, or not recognize it, so a no output. For example, in this case, if we start with a infinite string that we start from here, and we read the 1, so an infinite string like this, we read 1, we are here now in the computation. Now we read another 1, and we are here. We read a 0, we are at the bottom state here. And now we can read both 1, 0, and so everything will be the same. I mean, everything will be recognized. So we can recognize any strings that start with a 1, 1, 0, and anything that starts with a 1, 0 or a 0. But you can see that in this model here, which is nothing else than a graphic representation of what our machine is. So the red dots are the states, and the arrows represent the transition function, we cannot read the infinite string that starts with a 1, 1, 1. Now that we know what an automaton is, we want to find a bridge between automata theory and our geometric point of view. And the bridge are self-similar trees, because self-similar trees leads to a coding for the boundary of the tree. So we start again with our favorite hyperbolic tiling. We construct our tree. The tree of atoms works fine for us, but you can also imagine the one from Cornet and Papadopoulos. But now you want that the tree is self-similar. That means that you have a finite coloring on the vertices of the tree. And a color tells you how many children one vertex has, and which is the color of any child, sorry. So for example, here we have blue and red. A red vertex has 3 children, and all of them are blue, while a blue vertex has 2 children, one is blue and one is red. Starting from this, you can construct an automaton where the states are the colors. Okay, and you can code any edge in the tree, so that, like here, you can see that you have an infinite string on a finite alphabet for any boundary point in the tree. But now that we have our set of codings, since we are interested in groups, we want something that can rearrange them, permute them in some nice way, or if you want, in the same fashion as they were created. And so we need what is called a transducer, and asynchronous transducers, because we start again from the machine that we had before, the automaton, and we add an asynchronous output. So in this case, we have in input an infinite string, and in output, again, an infinite string. And the idea here is that if this is our input, string in input, and we start from x1, here is our initial state, then at each step of the computation, we will read one bit, and we will get finite strings on the alphabet. So here we read 1, and we get a 1, and we are in x0, so nothing changed. Here we read a 1, and we cancel out this 1 because here epsilon is the empty string. So this is the result in the computation. Now we are here. We read a 0, and so in output we have a 0, 1, so a string, not a 1 bit. This is why it's called asynchronous. And now that we are here, whenever we read a 1, we get a 1, and whenever we read a 0, we have a 0, and so nothing changed. So we just changed the prefix of this infinite string. And you can easily see that with this definition, you can model the action of groups onto infinite strings. For example, if you know it, in this case, this is the automaton for Thompson's group F, where x0 and x1 are the canonical as natural generators, I don't know what to call them. Okay, so why this tree of atoms was introduced in the first place? Well, because Belk, Blake, and Matucci found out that any element of an hyperbolic group can be seen as a transducer that acts on the coding of the boundary of such a tree of atoms. And the next step in this direction was, together with Zaremsky, they actually proved that this leads to an embedding of hyperbolic groups into finally present a simple group, and this is connected to the Bunigman conjecture that I mentioned before, and James was talking about in his talk. So these are two very nice results, but still we didn't know much about the or the connection between this tree of atoms and the hyperbolic literature. What we knew was that the boundary of this tree is homeomorphic to the Euro function boundary, and that there exists a Quotient map from this boundary onto the Gromov boundary, so as in the Korner-Papadopoulos case. But what we wanted was a nice description of the fibers, at least understand how big they were, an approximation of the Gromov boundary starting from these atoms, as in the natural case of geodesics, and maybe a machine that can determine whether two elements are in the same fiber or not. And so what I found out was that, I mean, this sequence of nested atoms that represent a boundary point in the tree of atoms are not that different from geodesic rays. First of all, we know that two of them are the same point in the Gromov boundary if and only if their Hausdorff distance at each step, I mean, these are subset of the graph, so we need to use the Hausdorff distance. The Hausdorff distance at each step is bounded by a constant that doesn't depend on the two elements that we were looking at. So is a fellow travel property in some sense, and this leads to the fact that fibers and the topological dimension of the boundary are bounded. But we also know that there's some generalized exponential divergence, because if these two boundary points do not glue, then they diverge exponentially as geodesic rays. What about approximation? We had two metric approximation. The first one is weak Gromov-Hausdorff convergence of all the levels in the tree to the Gromov boundary, while the second involved this so-called space of tips. The tip of an atom is just the collection of all the points that are closer to x0, the base vertex. And if you consider the tips of all the atoms in the tree, well, then you have a set, and you can endow it with the Hausdorff metric, because they are all subset of your graph. And you can see that this space is quasi-isometric to the original graph gamma. While I think that the most interesting approximation that I got was this one that is more combinatorial. You start from your tree, and you add suitable horizontal edges. You get what is called the graph of atoms. And the way you add these horizontal edges is just by exploiting the gluing theorem that I mentioned before. So you need a bounded distance between the two atoms in the graph. And what you can prove is that this graph of atoms, that is in some way look nicer than the original hyperbolic graph, is quasi-isometric to gamma. So the boundaries are homeomorphic. And this is something that was inspired by the work of Kajmanovic and Nekrashevich on self-similar groups. Let's see an example of horizontal graph. So what here is in the picture is in red, just to understand why we are calling this an approximation. So this is a hyperbolic group. We start from the first horizontal graph. All of these are atoms. We have two colors because we have two types of atoms. And if we focus on this piece here of the tetrahedron, then we have this. We forget about the colors, okay? And the second horizontal graph of this piece is this one. Then we have this one, and we can go on recursively, so that once we glue together the four pieces of the tetrahedron, then we get this result here. That is exactly the Gromov boundary of our hyperbolic group here. As a last remark, we say that a set of infinite string on a finite alphabet is called rational whenever it's recognized by an automaton. We have many examples of this rationality, self-similar trees as before, but also semi-Markovian spaces and the gluing relation of Leibniz spaces of contracting self-similar groups. And so here what we proved was that since the tree of atoms is self-similar, then we also have an automaton that can recognize whether two boundary points in the tree of atoms are the same or not. And here's the example for, again, our hyperbolic tiling. I think that's all. These are further direction in this theory. So we are trying to prove the same properties for Thompson's-like groups that are not acting on the Cantor set, obviously, and trying to simplify the proof of the embedding before, but also trying to get embeddings for other classes of group, and trying to define a limit set for subgroups of the rational group, as in the case of self-similar groups, using the approximation that I mentioned before. So thank you for the attention.
Okay, let's thank the speaker. Are there any questions for Davide?
Let's see. Okay.
Is that someone or any questions? Okay, I just want to clarify one thing with your definition of automata. So
Yeah.
with accepting infinite words, all of the states of the automata are accepting, is that right?
Yeah. I didn't mention that because
I mean, that's probably just me because I've seen other things, but yeah, that makes sense.
No, I mean, you can work towards the direction of Bucci, automaton, and stuff like that, but this is way more simpler. So let's forget about that. I mean, since we are accepting infinite strings and in this way, you just don't mention the exceptions, the state that accept, and just say that anyone is okay, and any state is okay for accepting. Yeah. Sorry.
Yeah. Thank you. Are there any other questions for the speaker? Okay, if there are no further questions, let's thank the speaker again.